All right, so first, we have finished our 4 classes on finances, so that's behind us now. We have 2 days left on fractals. Today is the first day. Then we have this to be announced day, more details on that next week. And then our review day for the third test is December 16th. Exam is actually on December 18th, which I think is 2 weeks from today. Is that right? All right, so this class will be completely finished 2 weeks from today. Regular start time for the exam, 1 o'clock until 2:15. It's regular tests, no longer than any of the other tests. In fact, probably a little shorter than the other tests. And the financial project is due on December the 9th, which is this coming Monday. So I've already gotten a handful of them turned in already. So if you have it, throw it in the folder there. If not, it's due Monday, and after Monday is when the lateness penalties start accruing. So try to get it done before then. Questions on that? Okay, so I know that that many of you guys are tired and sick and all that jazz. This is a very difficult time in the semester for many of our students. Oftentimes classes are culminating, and so there are a lot of responsibilities, and the material is as tough as it will be all semester. So if you have any hidden reserves of energy, this is the time to call on them. Right, 2 weeks from now, this class will be done, and most of your classes will be done. So whatever you can do to carve out some extra time, if you can shave a little bit of time at work and not work as many hours, or other responsibilities that you have, whatever you can do to really try to just focus and make one last big push for these next 2 weeks might make a big difference in terms of grades. All right, so I'm on page 24, but you guys are on page 25. I mentioned that there were some problems. The version of the packet that got sent to the printers wasn't actually the final version that should have been sent to the printers. So one of the problems is here in this class. So actually, if you guys can go a few pages away to find the learning objectives. What page is that for you? 31? And towards the end of the learning objectives inside of the textbook assignment, it references pages 1 and 2. Do you guys see that?
Well, mine says 3 and 4. 3 and 4, but sorry, 1, 2. Not yet. Yeah, you gave us 2 twos.
So when you say you gave us.
On the question numbers.
Okay. It should say 1 and 2.
Oh,
Should say 1 and 2.
Okay, so we got to change the 3.
Change the 3 and 4 to say 1 and 2. Yeah, so I have the correct version. You guys have a previous version. All right, and then speaking of edits to this packet, I mentioned that one of our classes coming up is our review day. And on that day, you guys will probably look at the sample test problems. Now, the sample test problems that you have some issues with them. So you can ignore the sample test problems that are in the big packet and instead use the little handout that I just gave you today. So we're not going to look at that together for a couple of classes. But if you're ready to start studying for that exam, use the sample test problems that I just gave you today. All right. There are videos for most of these problems already on YouTube, and they should all be up there pretty soon if they're not already. All right. Okay. So let's go back to page 25. And we'll start up here at the top. Nicole.
Lots of group work today, so let's get going. Fractals are geometric objects defined by a state procedures applied to the alpha at one step.
Thank you. Alicia.
We'll start our study of fractals with an example of the Koch Snowflake. We study this and other examples will develop some knowledge and vocabulary surrounding fractals in general.
Thank you. Sana? Okay, so we're about to define this kind of crazy shape that you guys are going to draw in a few minutes. It's called the Koch Snowflake. Starts with a basic equilateral triangle. Equilateral is a fancy word that means equal sides. In fact, lateral has to do with side, and so it really literally means equal sides. Okay, and then we go to Barb for B. Okay, so do you guys see that? You start with the basic triangle. You're going to then tack on to the middle of each side of the original triangle another equilateral triangle. How big is that supposed to be? Well, it's 1/3 the size of whatever the original one was. So it has to fit perfectly. You guys see what, like there, it's got to fit perfectly there. So that completely dictates how big that triangle is going to be. It's going to be 1/3. The length of the new triangles is always going to be 1/3 of the original. And so we tack them on and we get this 12-sided snowflake, 1, 2, 3, 4, etc. We count to 12. All right. Okay, and now we're back to Aileen. C. Okay, so for example, take a look at this guy from the previous step. We had that little triangle up there. We're then going to tack on a little equilateral triangle onto each of these sides. And down here, we're going to tack on little equilateral triangles to each of these sides. And that's what you can see here, and that's what you can see there. All right? Okay, and so then you just keep doing that. To every shape that you get, you always add a new equilateral triangle to every single side. So part D is the first several iterations. There's the seed, and then after step 1 was the 12-sided thing that we saw. And then step 2 we just saw up above, and then step 3, and step 4. And it really gets to the point where it's hard to distinguish. Like between step 3 and step 4, the new triangles are so small that they become hard to see with the resolution that we have. We'll go to Jake for E. Thank you. 4, Lila. Thank you. Kate. Okay, so let's take a quick look before you make a guess. So perimeter means what? It's how far you have to walk if you walk around it. So if the perimeter is 27, then how much is each side? Then they're each 9. So each of these guys here is 9, and that means that when you cut it up into 3 equal pieces, how much is each of the 3 pieces? They're each 3s, right? So when you tack on this triangle right here, it's 3 and a 3 and a 3 and a 3, yes? All right, and so how many sides were in that guy? Do you remember? There were 12 on that side, and each of them is 3. So how much is the perimeter there? 36. So the perimeter here was 27. This perimeter here is bigger. You added more stuff. The perimeter of the next one will be bigger still. So what I'd like you guys to do is make a guess as to what the perimeter is, not just at step 4, but if you did this forever. Is the perimeter at 40? Do you think the perimeter will be at 100? Do you think it'll be at 1,000,000? What do you think it'll be if we go forever? So just write something down. Don't even need to discuss with your neighbors. Just commit to some guess. What is the distance that you'd have to walk if you walked around this thing in its infinite state? All right, we have a guess. If you're still thinking about it, you're thinking too long. Just make a guess. 50, 100, million, some other number. No, if you go forever. If we go forever. Just write something down. Stop worrying about being wrong. Okay. Next question is number 6, and we'll go back to Brandon. Okay, thank you. Let's take a look. Same idea as before. But now what we'll do is think about area. So what was the magic number there? It was 35? Okay, so we're going to now assume that the area of the original is 35. Okay, the original triangle right there, I can actually cut into some different pieces. How can I cut this? 1, 2, all right, so if I cut each of these into thirds, I actually hadn't done this before, so I'm not sure if it's going to work, but we'll give it a shot. I draw here and here and here, and then maybe something in there, and then something in there. How's that look? Can you imagine that we have lots of little triangles in the original? How many are there? How many little triangles are in that picture that I've drawn? There are 9 altogether. You see it? Green was perhaps not the best choice. I'll try this in red. There, 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 and then the original. 9 triangles in there. And if I drawn it a little bit better, you would actually see that each of those 9 triangles is the same as this one little triangle that we're sticking on. There's 9 copies of that guy, all right? Okay, I said here the area was 35. I'm just going to tweak it a little bit to make the number nicer. If it's 36 and it's made up of those 9 little red triangles, then what's the area of each of those red triangles? Yeah, there's 4. It's 4 each, right? So this is a 4, and this is a 4, and this is a 4. So how much area did we just add to the picture? We just added 12, and we had 36 already, and so the new area is 48. That is true. And then you're going to tack on these little guys here. Now the areas of those are smaller, right? They're not as big as the 4s, so maybe they're 1s or halves or something like that. But you're going to tack on a whole bunch of them. And so you're going to add some more area, right? It's got to be more area than it was before. You added some space. So if we let this process go forever, I want you to make a guess and just write it down. What do you think the area of the infinite version of this Koch snowflake is? It goes from 36 to 48 to something bigger still. Is it going to get to 50? Is it going to get to 100? Is it going to get to 1,000,000? Write something down. Area of the infinite version. Okay, everybody's got something written down. No more thinking, just commit to some number. Yes, I can. Okay, we'll go back to Evan for the next one.
Are we on set?
Go ahead, Evan. Okay, so the Koch snowflake, we are looking at just a tiny piece of it out here, right? Just this really bumpy thing. You can imagine that's a part of the Koch snowflake. And if you zoom in on just that little space there, and you blow it up, you get this thing here. Does that seem reasonable? Just looking at like that little thing in there becomes this big thing here, which looks an awful lot like what? Like the previous thing. And if you zoom in on this little guy right in here, which came from maybe just like the tip, right? Just this little teeny tiny piece of the original. This teeny thing gets blown up to here, which gets magnified to here. And what does that look like? The original again. And it's really kind of freaky, but no matter how much you zoom in, it just keeps looking like exactly the same thing. And so back in your high school geometry class, you probably saw the word similar. 2 shapes are similar if they have the same size, same shape, but different sizes. So this thing right in here is just a smaller version of exactly the same shape. All right, we might come back to that video, but we're going to skip it for right now. Let's go to 8. Ed? Thank you. Mary? Okay, so what is this first picture? So probably the pictures on the board are nicer to look at than the ones on your paper. So what is this first one a picture of? Looks like a fern. Suppose that I were to just show you this part of the fern, but really magnified, so you didn't have the rest of the fern to compare to. What would you say this thing is if that's all you saw? You'd probably say, oh, that's a fern, right? Doesn't it look like a fern? Just tilt your head a little bit. And okay, it might end at that point, but if the fern is big enough, then maybe it's got even one more layer of self-similarity. So all these pictures are supposed to illustrate that there are plenty of things in nature which are self-similar. If you just zoom in, pretty much looks like it did on the surface. Anybody know the name of this thing? Evan is an expert.
It's on the bottom of the screen.
Don't ruin his thunder. All right, so this is an edible vegetable, and it looks really strange, but if you zoom in on maybe this top thing right up here, you get something a little bit bigger. And what does that look like? If I just showed you this thing, so it looks like the original, right? And so again, if you just kind of keep zooming in on these little guys, they look pretty much like the big guy does. Anybody seen that one before? It's a fiddlehead, right? It's another kind of fern, also edible. What's that? Good sauteed, yes. And so that's it. And if I were just to show you this piece right here without any other context, and you knew what this thing looked like, you'd say, oh, it's a fiddlehead fern, right? What is going on in this picture here? Yeah, looks like ice, right? It's just a big set of glaciers and lots of little kind of river-looking things. But if I just zoomed in on this thing, you wouldn't say, oh, that's just part of some ice thing. You just say, look, it looks like some ice that's breaking. And if I zoomed in on, say, like this little part right here, but just gave you a very detailed, focused picture, you'd say, oh, it just keeps looking similar. Not exact, but quite similar. And then finally, lightning. If you look at just this thing here, what would you say it is? Lightning. And if you look at just this guy right here with enough detail, you'd say, oh, it's just lightning. All right. Let's move on to the activity. Okay, if you have a pencil, you're going to want to use it on this activity. Let's we're gonna do just a tiny bit of it together before you guys dive in with your neighbors. Did everybody read? Brandon, did you read? Yes, everybody back there. Yes. Casey, part A, please. Okay, so go on to the next page. And starting somewhere down towards the bottom, maybe in here-ish, just pick a random point. Doesn't have to be exactly that one. Don't make it too close to an edge. You want a little bit of space for this shape to expand. And we're going to make a triangle that has sides of length 9. So very carefully count 1, 2, 3, 4, 5, 6, 7, 8, 9, and put a dot so that you have a length of 9 altogether. And if you happen to have a straight edge, that's a good time to use it to connect those two dots. So that's going to be the bottom side of our triangle. Use a straight edge if you have access to one. Somebody can use the folder at each table. Okay, and then what we're going to do is make the rest of this equilateral triangle. Again, that's the bottom. So counting up at an angle, again, you want to count to 9. So I can't fit it all. I want to make sure we have some of the context of this on the board here. So very carefully count 9 at an angle and put a dot up there at the top after you've got 9, a side length of 9. And then you should be able to just connect the last two dots to finish your equilateral triangle. Okay, and then you just connect the dots, hopefully with the pencil if you have. Okay, you can stay where you are. Actually, you got to go back a page because we're going to fill in something in this row here. So part B says fill in the first row of the table below. So we're going to start to calculate some stuff. So this activity involves two things. You're going to draw, but you're also going to calculate, and then we'll analyze both at the end. So the first row of this table talks about the seed. Apparently M is what we're going to use for the number of sides on the Koch snowflake. So how many sides in the seed? 3. It's just a triangle. L will be the letter we use for the length of each side. Each side is length 9. And then what was the perimeter of the whole thing? 27. 3 times 9 will give us the perimeter. Then what we're supposed to do is here in C, it says step 1 of the Koch Snowflake. On each side of the seed triangle, draw an equilateral triangle that has side length 3. So I'll just draw it here on the bottom, but I'm going to cut my bottom side into 3 equal pieces. But the whole thing was 9, so how much is each piece? It's 3. So I'm going to go 1, 2, 3. I'm going to put a little dot there, or maybe a dot. 1, 2, 3, a little dot there. 4, 5, 6, a little dot there. 7, 8, 9 is the end. And so then this thing right here in red is one side of my new equilateral triangle, which means all the sides are 3. So what we're going to do is we're going to go down at an angle, 1, 2, 3, and put a dot. 1, 2, 3. Everybody see that new dot? It's 3 at an angle from either of the ends. And then I'll draw those guys in blue. And that's what goes on the bottom. And so you're going to draw a new equilateral triangle on all 3 sides of your original. And you want to make sure that you put it in the middle. So instead of putting it there. Oh, I see. Yeah, so go ahead and draw all 3 of these new triangles. Go back to the table and fill in the next row where you start calculating number of sides, length of each side, and perimeter. And according to the directions, you guys are supposed to get up to step 4. You are currently filling in step 1. The seed doesn't count, or you can call it 0 if you want. You're filling in step 1. You need to get to a 4. So go back and forth between the table and the graph. Raise a flag if I can help. Okay, so I recognize that groups are in different places right now. We're going to move on, but we're just going to talk about some highlights to try to bring everybody back together regardless of where the groups were. In packet 2 on page 34 were some relevant formulas that talk to you about how to write down recursive and explicit rules when you had an exponential growth example. An exponential just means you keep multiplying by the same amount, and that's what we saw in our table here. So I've written them here. They aren't written out in the packet anyplace. Well, they actually are in summary. So you don't need to like copy these formulas down, but hopefully they make sense if you have that other packet page open in front of you. But once you have the numbers, once you have the formulas, you can use them to answer harder questions. Like if the seed has a side of length 9 and we want to go to the 10th step, I don't want to have to fill in the whole table to get what's in the 10th row. And so we can just use this guy right here and work our way through, right? So this says that if you want the 10th number, you just take 27 and multiply by the magic 4/3 raised to the 10th power. And some people have done this. Was it 479? Yeah. So the perimeter there is 479. And if you keep going forever, infinite number of iterations, every time that perimeter gets multiplied by 4/3, what happens if you do it forever? What does that number become? Infinity. The perimeter becomes infinitely large, which is kind of surprising. I asked you guys to commit to an answer to this before. I said if the perimeter is 27 to start with, what happens if you go forever? I said, is it 50? Is it 100? Is it 1,000,000? It's infinite. Even though the infinite version doesn't look terribly different from this thing, it doesn't like sprawl out forever, right? It'll never like creep, it'll never like creep out to this way and then come back in. But somehow it's infinite if you just go forever, even though it occupies a small space. It would take forever to walk around this lake if we let it get to the infinite Koch snowflake. Okay, so we talked about perimeter, but let's also talk about area. And in order to talk about area, we need a fact. And it's a formula for the area of a triangle. Anybody know any formula for the area of a triangle? Half base times height. Have we heard of that one before? Yeah, area of a triangle is half the base times the height. So that's fine, provided you know the base, which we're just calling S here, and the height. Unfortunately, we don't have the height in this example. It's just an equilateral triangle. So I'm not going to go through the details of where this formula comes from, but it's a special case of that half base times the height for an equilateral triangle. Turns out the area of that triangle right there is s squared. S is the area, is the length of one side, times this funny number, root 3 divided by 4. S squared times the square root of 3 divided by 4. No justification. You just have to trust me on this one. So, for example, if we had a triangle, what was the original side for us? 9. And I want to find the area of this triangle. What's getting squared? S, which is how much in this triangle? 9. So we go 9 squared times root 3 over 4, which is 81 times root 3 divided by 4. Okay, I'd like to be able to get this as a decimal. So 81 square root of 3. Make sure you close those parentheses if your calculator puts them in, and then divided by 4, and we get about 35. So the area of our starting triangle is about 35 square units. Okay. All right, so on the next page, we're going to fill in this table where we try to calculate the area of the snowflake at each stage. All right, let's take a look at the first row, which has already been filled in. So first thing we're doing is just numbering. So we'll look at the seed to start with. What's the side length of the original triangle? 9. How many triangles are there? Just the one originally. What's the area of that triangle? We just found it. It was the 35.07 using the crazy formula, okay? You're going to have to use that crazy formula. Okay, that 35.07 is the entire area of the picture at that stage, and the area of the snowflake is about 35.1, just rounding it. Then we're going to tack on some triangles, all right? So, step 1, what's the side length of the new little triangles that get tacked on? They were originally 9. What's the next triangle size?
3.
Is 3. So the side length of the triangles is all 3. How many triangles did you stick on? How many triangles did we tack on? We tacked on 3 originally. You had a big triangle and you stuck on 1, 1, and 1. So you tacked on 3 triangles. That's the number that you attached. It happens these two are both 3, but that's just a coincidence. One of them is the side length of the triangle. The other one is how many triangles you stuck on. Now, in order to get this number right here, the area of each triangle that we attach, all we have to do is go to our magic formula. It should be s squared times root 3 over 4. S was 9 in this case. So 9 squared became 81. But what's the side length at this stage is a 3. So instead of doing 9 squared, it should be 3 squared. So s squared root 3 over 4 is our magic formula. And if we let s equal 3, which it is in this row, then it becomes 3 squared, or 9 root 3 over 4. 9 square root of 3 divide 4. That's the number in the table. So each of the little triangles we just tacked on has an area of about 3.9. Now, how many of those triangles did we tack on? 3 of them. So if I want to know how much area I added, what do? We're going to multiply, right? Because you have 3 triangles that each have an area of about 3.89. And when you multiply by 3, you get this 11.69 number. Yes? Now, we previously had 35.1 was the area of the original triangle. You just added 11.69 new area, new stuff. So what do I do to find the total area at that stage? Is we just add these two together. So we're going to add that to the 35.07. 46.76 is the total area at that step. And I'll round it to the nearest tenth, 46.8. Okay, let's do one row together now. Everything has been filled in for us so far. Let's look at the next stage. Here we go. So we're looking at step 2. You stay where you are, but I'm going to come back and show you the picture for step 2. Where's our picture for step 2? Here we go. So step 2 was this guy here at the bottom. So the first question, first thing in your table here is the side length. Original side was 9. Then these guys were how much? 3. And then these little guys are 1. 1/3 will be the next one. But 1 is the first number you're putting in that blank. The side length is now 1. And the next number we want is the number of triangles. So here is one triangle, the number that we added. There's 1. There's another one. You need to find those guys. Here's another one. But notice I'm going to put here in black. This triangle is not part of the calculation because that was there already. We're only looking at the ones that we tacked on. And now I'll scroll up just a little bit so you can see what it was. We're comparing that top right picture to this bottom one. So I want to know how many green triangles do we add? It's 12. If you count them very carefully, you will see you added 12. So 12 is the number in the next blank.
Yeah.
And then we need to know the area of each of those 12 little triangles. So again, we're using our s squared root 3 over 4. How much is the s for these little triangles? They're each 1. So we're going to do 1 squared, which is just 1, times root 3 divide 4. Details. 0.433. What does that represent? That's the area of each of these little tiny triangles, 0.433. And we had 12 of them. So that's the area of one of them. And then we multiply by the 12 of them that we added. And so that means we add about 5.2 square units of new triangles. That goes in the next blank. And then you add that to what number? To the 46.8, because that's what we had. And we just added some more triangles, so we're just adding area. So rounding this to the nearest tenth is 52.0. Right? So that's the area at that stage. Now, there's patterns here. You don't need to rely on the picture because it's a lot of the same numbers that you had in your previous table. So in the first column, which is the side lengths, what's happening to the side lengths every time? How do you go down the column? You divide by 3 every time. You found that pattern already. What's happening in the next column, which is the number of triangles attached? It's times 4. You found that already. So you guys know how to fill in a lot of this. Really the only new thing is this magical s squared root 3 over 4. And then just careful keeping track of the data. All right, let's see how far we can get here.